Welcome back. In the last video, we saw visualizations of the cost function j and how you can try different choices of the parameters w and b and see what cost value that gets you. It would be nice if we had a more systematic way to find the values of w and b that result in the smallest possible cost, j of wb. It turns out there's an algorithm called gradient descent that you can use to do that. Gradient descent is used all over the place in machine learning, not just for linear regression, but for training, for example, some of the most advanced neural network models, also called deep learning models. Deep learning models are something you learn about in the second course. So learning this tool of gradient descent will set you up with one of the most important building blocks in machine learning. Here's an overview of what we'll do with gradient descent. You have the cost function j of wb right here that you want to minimize. In the example we've seen so far, this is a cost function for linear regression, but it turns out that gradient descent is an algorithm that you can use to try to minimize any function, not just a cost function for linear regression. Just to make this discussion on gradient descent more general, it turns out that gradient descent applies to more general functions, including other cost functions that work with models that have more than two parameters. So, for instance, if you have a cost function j as a function of w1, w2, up to wn and b, your objective is to minimize j over the parameters w1 to wn and b. In other words, you want to pick values for w1 through wn and b that gives you the smallest possible value of j. It turns out that gradient descent is an algorithm that you can apply to try to minimize this cost function j as well. What you're going to do is just start off with some initial guesses for w and b. In linear regression, it won't matter too much what the initial values are. So a common choice is to set them both to 0. So for example, you can set w to 0 and b to 0 as the initial guess. With the gradient descent algorithm, what you're going to do is you'll keep on changing the parameters w and b a bit every time to try to reduce the cost j of wb until hopefully j settles at or near a minimum. One thing I should note is that for some functions j that may not be a bow shape or a hammock shape, it is possible for there to be more than one possible minimum. Let's take a look at an example of a more complex surface plot j to see what gradient descent is doing. This function is not a squared error cost function. For linear regression with the squared error cost function, you always end up with a bow shape or a hammock shape. But this is a type of cost function you might get if you're training a neural network model. Notice the axes. That is w and b on the bottom axes. For different values of w and b, you get different points on this surface j of wb, where the height of the surface at some point is the value of the cost function. Now, let's imagine that this surface plot is actually a view of a slightly hilly outdoor park or a golf course, where the high points are hills and the low points are valleys like so. And I'd like you to imagine, if you will, that you're physically standing at this point on the hill. And if it helps you to relax, imagine that there's lots of really nice green grass and butterflies and flowers. It's a really nice hill. And your goal is to start up here and get to the bottom of one of these valleys as efficiently as possible. So what the gradient descent algorithm does is you're going to spin around 360 degrees and look around and ask yourself, if I were to take a tiny little baby step in one direction, and I want to go downhill as quickly as possible toward one of these valleys, what direction do I choose to take that baby step? Well, if you want to walk down this hill as efficiently as possible, It turns out that if you're standing at this point in the hill and you look around, you may notice that the best direction to take your next step downhill is roughly that direction. Mathematically, this is the direction of steepest descent. And it means that when you take a tiny baby little step, this takes you downhill faster than a tiny little baby step you could have taken in any other direction. So after taking this first step, you're now at this point on the hill over here. Now let's repeat the process. Standing at this new point, you're going to again spin around 360 degrees and ask yourself, in what direction would I take the next little baby step in order to move downhill? And if you do that and take another step, you end up moving a bit in that direction, and you can keep going. From this new point, you can again look around and decide what direction would take you downhill most quickly. Take another step, and so on, until you find yourself at the bottom of this valley at this local minimum right here. What you just did was go through multiple steps of gradient descent. It turns out gradient descent has an interesting property. Remember that you can choose a starting point at the surface by choosing starting values for the parameters w and b. When you performed gradient descent a moment ago, you had started at this point over here, right? Now, imagine if you try gradient descent again, but this time you choose a different starting point by choosing parameters that place your starting point just a couple steps to the right over here. If you then repeat the gradient descent process, which means you look around, take a little step in the direction of the steepest descent, so you end up here, then you again look around, take another step, and so on. And if you were to run gradient descent the second time, starting just a couple steps to the right of where we did it the first time, then you will end up in a totally different valley, this different minimum over here on the right. The bottoms of both the first and the second valleys are called local minima, because if you start going down the first valley, gradient descent won't lead you to the second valley, and the same is true if you started going down the second valley. You would stay in that second minimum and not find your way into the first local minimum. So this is an interesting property of the gradient descent algorithm, and you'll see more about this later. So in this video, you saw how gradient descent helps you go downhill. In the next video, let's look at the mathematical expressions that you can implement to make gradient descent work. Let's go on to the next video. Let's take a look at how you can actually implement the gradient descent algorithm. Let me write down the gradient descent algorithm. Here it is. On each step, w, the parameter, is updated to the old value of w minus alpha times this term d over dw of the cost function j of wb. So what this expression is saying is, update your parameter w by taking the current value of w and adjusting it a small amount, which is this expression on the right, minus alpha times this term over here, okay? So if you feel like there's a lot going on in this equation, it's okay, don't worry about it, we'll unpack it together. First, this equal notation here. Notice I said we're assigning w a value using this equal sign. So in this context, this equal sign is the assignment operator. Specifically, in this context, if you write code that says a equals c, it means take the value of c and store it in your computer in the variable a. Or if you write a equals a plus 1, it means set the value of a to be equal to a plus 1, or increment the value of a by 1. So the assignment operator in coding is different than truth assertions in mathematics, where if I write a equals c, I'm asserting, that is, I am claiming that the values of a and c are equal to each other. And hopefully I will never write a truth assertion A equals A plus 1 because, that just can't possibly be true. So in Python and in other programming languages, truth assertions are sometimes written as equals equals. So you may see code that says A equals C if you're testing whether A is equal to C. But in math notation, as we conventionally use it, like in these videos, the equal sign can be used for either assignment or for truth assertion. And so I'll try to make sure it's clear when I write an equal sign, whether we're assigning a value to a variable or whether we're asserting the truth of the equality of two values. Now, let's dive more deeply into what the symbols in this equation means. The symbol here is the Greek alphabet alpha, and in this equation, alpha is also called the learning rate. The learning rate is usually a small positive number between 0 and 1, and it might be, say, 0.01. What alpha does is it basically controls how big of a step you take downhill. So if alpha is very large, then that corresponds to a very aggressive gradient descent procedure where you're trying to take huge steps downhill. And if alpha is very small, then you'll be taking small baby steps downhill. We'll come back later to delve more deeply into how to choose a good learning rate alpha. And finally, this term here, that's the derivative term of the cost function j. Let's not worry about the details of this derivative right now, but later on you get to see more about the derivative term. But for now, you can think of this derivative term that I drew a magenta box around as telling you in which direction you want to take your baby step, and in combination with the learning rate alpha, it also determines the size of the steps you want to take downhill. Now, I do want to mention that derivatives come from calculus, and even if you aren't familiar with calculus, don't worry about it. Even without knowing any calculus, you'll be able to figure out all you need to know about this derivative term in this video and the next. One more thing. Remember your model has two parameters, not just w, but also b. So you also have an assignment operation to update the parameter b that looks very similar. B is assigned the old value of b minus the learning rate alpha times this slightly different derivative term d over db of j of wb. So remember in the graph of the surface plot where you're taking baby steps until you get to the bottom of the valley? Well, for the gradient descent algorithm, you're going to repeat these two update steps until the algorithm converges. And by converges, I mean that you reach the point at a local minimum where the parameters w and b no longer change much with each additional step that you take. Now, there's one more subtle detail about how to correctly implement gradient descent. You're going to update two parameters, w and b, right? So this update takes place for both parameters, w and b. One important detail is that for gradient descent, you want to simultaneously update w and b, meaning you want to update both parameters at the same time. What I mean by that is that in this expression, you're going to update w from the old w to a new w. And you're also updating b from its old value to a new value of b. And the way to implement this is to compute the right side, computing this thing for w and b, and simultaneously at the same time, update w and b to the new values. So let's take a look at what this means. Here's the correct way to implement gradient descent, which does a simultaneous update. This sets a variable temp w equal to that expression, which is w minus that term here. Let's also set another variable, temp b, to that, which is b minus that term. So you compute both right-hand sides, both updates, and store them into variables temp w and temp b. Then you copy the value of temp w into w, and you also copy the value of temp b into b. Now, one thing you may notice is that this value of w is from before w gets updated. Here, notice that the pre-update w is what goes into the derivative term over here, okay? In contrast, here's an incorrect implementation of gradient descent that does not do a simultaneous update. In this incorrect implementation, we compute temp w, same as before. So far, that's okay. And now, here's where things start to differ. We then update w with the value in temp w before calculating the new value for the other parameter b. Next, we calculate temp b as b minus that term here. And finally, we update b with the value in temp b. The difference between the right-hand side and the left-hand side implementations is that if you look over here, this w has already been updated to this new value, and it's this updated w that actually goes into the cost function j of wb. It means that this term here on the right is not the same as this term over here that you see on the left. And that also means this temp b term on the right is not quite the same as the temp b term on the left, and thus this updated value for b on the right is not the same as this updated value for variable b on the left. The way that gradient descent is implemented in code, it actually turns out to be more natural to implement it the correct way with simultaneous updates. When you hear someone talk about gradient descent, they always mean the gradient descent where you perform a simultaneous update of the parameters. If, however, you were to implement non-simultaneous update, it turns out it will probably work more or less anyway, but doing it this way isn't really the correct way to implement it. It's actually some other algorithm with different properties. So I would advise you to just stick to the correct simultaneous update and not use this incorrect version on the right. So that's gradient descent. In the next video, we'll go into details of the derivative term, which you saw in this video, but that we didn't really talk about in detail. Derivatives are a part of calculus. And again, if you're not familiar with calculus, don't worry about it. You won't need to know calculus at all in order to complete this course or this specialization, and you have all the information you need in order to implement gradient descent. Coming up in the next video, we'll go over derivatives together, and you come away with the intuition and knowledge you need to be able to implement and apply gradient descent yourself. I think that'll be an exciting thing for you to know how to implement. So let's go on to the next video to see how to do that. Now let's dive more deeply into gradient descent to gain better intuition about what it's doing and why it might make sense. Here's the gradient descent algorithm that you saw in the previous video. And as a reminder, this variable, this Greek symbol alpha, is the learning rate. And the learning rate controls how big of a step you take when updating the model's parameters w and b. So this term here, this d over dw, this is a derivative term. And by convention in math, this d is written with this funny font here. And in case anyone watching this has a PhD in math or is an expert in multivariate calculus, they may be wondering, that's not the derivative, that's the partial derivative. And yes, they'd be right. But for the purposes of implementing a machine learning algorithm, I'm just going to call it derivative, and don't worry about these little distinctions. So what we're going to focus on now is get more intuition about what this learning rate and what this derivative are doing, and why, when multiplied together like this, it results in updates to parameters w and b that make sense. In order to do this, let's use a slightly simpler example where we work on minimizing just one parameter. So let's say that you have a cost function j of just one parameter w, where w is a number. This means that gradient descent now looks like this. W is updated to w minus the learning rate alpha times d over dw of j of w. and you're trying to minimize the cost by adjusting the parameter w. So this is like our previous example where we had temporarily set b equal to 0. With one parameter w instead of 2, you can look at two-dimensional graphs of the cost function j instead of three-dimensional graphs. Let's look at what gradient descent does on this function j of w. Here on the horizontal axis is parameter w, and on the vertical axis is the cost j of w. Now let's initialize gradient descent with some starting value for w. Let's initialize it at this location. So imagine that you start off at this point right here on the function j. What gradient descent will do is it will update w to be w minus learning rate alpha times d over dw of j of w. Let's look at what this derivative term here means. A way to think about the derivative at this point on the line is to draw a tangent line, which is a straight line that touches this curve at that point. In math, the slope of this line is the derivative of the function j at this point, and to get the slope, you can draw a little triangle like this. And if you compute the height divided by the width of this triangle, that is the slope. So, for example, the slope might be, 2 over 1, for instance. And when the tangent line is pointing up and to the right, the slope is positive, which means that this derivative is a positive number, so is greater than 0. And so the updated w is going to be w minus the learning rate times some positive number. The learning rate is always a positive number. So if you take w minus a positive number, you end up with a new value for w that is smaller. So on the graph, you are moving to the left. You're decreasing the value of w. And you may notice that this is the right thing to do if your goal is to decrease the cost j, because when we move toward the left on this curve, the cost j decreases and you're getting closer to the minimum for j, which is over here. So far, gradient descent seems to be doing the right thing. Now, let's look at another example. Let's take the same function j of w as above, and now let's say that you initialize gradient descent at a different location. Say by choosing a starting value for w that's over here on the left. So that's this point on the function j. Now, the derivative term, remember, is d over dw of j of w. And when we look at the tangent line at this point over here, the slope of this line is the derivative of j at this point. But this tangent line is sloping down and to the right. And so this line sloping down and to the right has a negative slope. In other words, the derivative j at this point is a negative number. For instance, if you draw a triangle, then the height like this is -2 and the width is 1. So the slope is -2 divided by 1, which is -2, which is a negative number. So when you update w, you get w minus the learning rate times a negative number. And so this means you subtract from w a negative number, but subtracting a negative number means adding a positive number, and so you end up increasing w. Because subtracting a negative number is the same as adding a positive number to w. So this step of gradient descent causes w to increase, which means you're moving to the right of the graph, and your cost j has decreased down to here. And again, it looks like gradient descent is doing something reasonable. It's getting you closer to the minimum. So hopefully, these last two examples show some of the intuition behind what the derivative term is doing and why this helps gradient descent change w to get you closer to the minimum. I hope this video gave you some sense for why the derivative term in gradient descent makes sense. One other key quantity in the gradient descent algorithm is the learning rate alpha. How do you choose alpha? What happens if it's too small or what happens if it's too big? In the next video, let's take a deeper look at the parameter alpha to help build intuitions about what it does, as well as how to make a good choice for a good value of alpha for your implementation of gradient descent.